So let me summarize the day before the talk, because I was asked by Yehuda. So far we talked about basic tools like one-way functions and pseudo-random generators and pseudo-random permutations, pseudo-random functions. Now we're going to talk about encryption and MACs. And in the following days we are going to use the most important thing to remember from today is the definitions, right, or the concepts, the basic notions that we have. What are the basic objects that we are talking about? And today we talked about them from a theoretical perspective, but once you have a definition of the object, then you can start from I don't know, practical implementation or use it in a different context, as long as you understand what is the object, right? So that's the bottom line of today. If you have to choose one thing that you have to remember, is what are the basic notions that we have, what are the basic objects. Okay, so we saw that there are hills and the mountains, and Yiftach mentioned the cable car that goes to the mountain, but let me convince you that it's worth going up, right? So you can ski, right? You can do something, you can have fun on the mountain. So seriously, we had all these notions. These notions are nice as tools, and they are good abstractions, but eventually you want to do something useful, right? I mean, and typically when you wake up in the morning, you don't really want to generate pseudo-random bits, right? At least, I guess most of you don't. But you do want to encrypt or to authenticate, and that's what we're going to do. Okay, so let's talk business, so encryption. So I should say, by the way, that some of these slides are based on slides which were made by Benny Shaw. So I'd like to thank him for allowing me using some of these slides. Some of them are not, so the broad slides are mine probably. So, okay. So this is the basic setting. It's quite ancient. We have Alice and Bob and Eve in the middle, and she listens to the conversation. And in general, Alice wants to transmit some secret message, and right, the goal is to communicate secretly, and the means is a secret key. So these guys share a secret key. We don't know how they got this key, but maybe they met, maybe they did something else, but today, right in the beginning of the conversation, they have this secret key. And they want to use this key somehow to garble the messages in a way that Eve will not be able to understand them. Right? So this is a very old, I don't know, setting. It's much older than pseudo-random functions, pseudo-random permutation, and pseudo-random generators. It's almost as old as humanity, right? Since people were able to write things or to communicate, they had secrets and they wanted to communicate them secretly. So this is a very basic notion. And when we try to think or formulate a security, we can think of many different goals. Like, for example, one goal is that the adversary should not be able to learn the message exactly, right? So what do you think about this requirement? It's definitely good, right? It's a reasonable thing to ask, but is it good enough? So it seems to be a minimal requirement, but it doesn't look sufficient. So, you know, maybe the adversary cannot learn the message as a whole, but he can learn, say, I don't know, half of the bits of the message. Does such a scheme, is it secure or not? So it doesn't sound like something which is secure, so let's try to shoot for something stronger. So maybe you can ask that no adversary should be able to learn any meaningful information about the message. This sounds good, right? So, I don't know, if you're an engineer, as I am, so you say meaningful information, it looks great, right? You have information in the slide, so it looks very good. What's the problem with this definition?
How do you define meaningful?
Right, how do you define meaningful, right? So when you construct your scheme, it's not clear what will be meaningful, right? I mean, does it mean that, I don't know, the parity of the bits? Right? One bit that equals to the parity of all the bits of the message. Is it meaningful or not? It can be meaningful, right? I mean, maybe, you know, all the adversary wants to know if I'm sending like a message which is yes or no, right, to some question. And the parity of the bits of these two messages differ. So if I leak a single bit here, the parity of the message, it will learn everything. So when I'm designing a scheme, I really don't know what is meaningful. And in fact, even when I'm using a scheme, as a user of an encryption scheme, it's not clear to me what is considered to be meaningful by the adversary. Right? Because I just want to hide my messages and I'm not sure what the adversary is trying to do. Right? Maybe he's trying to achieve some, I don't know, to apply some very strange attack on me and all the other people in the room that will allow him to do something strange, right? So it's very hard for me as an honest user, and even harder for me as an engineer, to design a scheme which hides all meaningful information. I don't know what's meaningful and what's not. So we're going to shoot for something which is stronger. Just, I want to hide any information about the message, right? So this sounds at least intuitively a good notion, and it's not clear right now how to formalize it mathematically, right? There are other important questions, like what are the adversary's capabilities, right? I mean, is the adversary passive or active, right? If he's sitting on this line, can she modify messages or just listen to them, right? And maybe she has some prior information. For example, in the story that I just told you, the adversary knows that one of the messages is going to, that the message is going to be either yes or no. So it has some prior distribution on these messages, right? I mean, does he have some such a prior information or not? Also, you should ask what are the adversary's computational resources. Is it computationally bounded? Maybe it has some bound space that he can use right on the memory. Maybe there are some limitations which are related to adaptiveness or things like this. So we have to specify exactly what kind of adversaries should we are trying to defeat. And you can answer all these questions in different ways, and you'll get different notions of security. So this goal, encryption, is a very rich notion, and you can have many different definitions, and we have different definitions for security. So we're going to see some of them, not all of them, definitely. And at the background, we have this high-level meta question, right? How to define, how to formalize this secrecy in a mathematical way? Because eventually you want to prove theorems, and if you want to prove a theorem, you better have a well-defined notion of security. And this is where, you know, where there is a big difference between the old theory of cryptography, like in the ancient days, or even like 100 years ago, compared to modern cryptography, where we actually formalize these notions of secrecy and hiding information in a well-defined way, which allows us to argue about them and prove theorems about them, right? So there is a very big, I don't know, a very big difference between being able to talk about these things like hand-waving and being able to prove theorems or formalize them mathematically. Okay, so let's leave these questions for now, and let's talk about the syntax, so it should be easier. So an symmetric encryption scheme consists of a pair of algorithms. So the first algorithm is just an encryption algorithm. So usually I'm going to use E to denote this encryption algorithm. It takes this key, secret key, with a string, and a plain text, a message, right? Another string, and it outputs a ciphertext. Okay, the ciphertext is an encrypted message. I'm going to use this E subscript K, the key is in the subscript and the message in the parentheses. But eventually it's a function of both the key and the message, right? And in addition, I want a decryption algorithm, naturally. So this decryption algorithm takes the key and the ciphertext C, and it outputs the plain text. And again, I'm going to put the key in the subscript. Okay. So this is decryption. And the basic property that I want is, before secrecy or security, right, correctness, right? I want this thing to work well. So for every message and every key, if you encrypt the message using this key and then you decrypt it, you'll get the same message, right? Okay, good. And I should know that both algorithms are by default efficient, so they run in a probabilistic polynomial time, and they may be randomized. So in addition to the message and the key you can use some random coins, okay? Which means that this thing, we usually write this, but actually what we have here is not a single value, but a distribution over values, right, if you use some random coins. This distribution is induced by the choice of the coins of the encryption algorithm, right? And similarly for the decryption. Okay. And so far we didn't talk about secrecy at all. So questions about this? It can, but it seems weird, right? So it can be randomized. I'm not saying that it's not in the. I don't disallow it in the definition. But if I require that this thing should hold always, then you can always just fix some randomness to the decryption algorithm, like the all-zero string, and then you'll get you de-randomize the decryption algorithm. So without loss of generality, you can always assume that the decryption is deterministic. Right? If you require this thing to hold for every message and every key, as I do in this talk. Mm-hmm.
Does Pinkas have access to the conflicts of randomization?
No. So we'll have to say exactly what Eve knows and does not know, but in general, my coin tosses are private. So Eve can see the ciphertext, and if I include some of the coins in the ciphertext, then she can see it, right? And sometimes we'll do that. But in general, when I toss a coin, I can toss it privately and then use it in a private way, right? Okay. Okay, so what is secrecy? So we're going to define secrecy by using the notion of indistinguishability. Again, this is maybe very clear now because we had all these talks about indistinguishability, but it's a huge breakthrough, right? I mean, being able to formalize secrecy, right? The fact that you can't learn anything about a message, just saying that the encryption of two messages should be indistinguishable, right? So what is a good custom? A good custom is a custom which when you put it on two different people, they look the same, right? So a good encryption is an encryption which, when it's invoked on two different messages, you can distinguish between the two. Right? This is our intuitive notion, and now let's try to be more careful about formalizing it. But that is going to be our basic framework, indistinguishability. Okay. So here's the definition of perfect secrecy. So it goes back to Shalom, although Shalom didn't use this formalization, he used an equivalent one. So what is secrecy? So for every pair of messages, M0 and M1, of equal length, the ciphertext C1 and C0 should be identically distributed. So think of two experiments, right? So here's the experiment 0. I'm going to choose a random key and then output the encryption of M0 using this key. And a different experiment where I choose a random key and then I'm going to output the ciphertext of M1. Okay? So the output here is a random variable, right? Whose distribution is induced by the choice of the random key. Okay? And this definition, originally due to Shannon, says that these two random variables should be identically distributed. Okay? So it's a very strong definition. In particular, it says that even if when you look at this ciphertext, even when you have unbounded computational power, you cannot distinguish them. And note that the quantifier is for every pair of the different messages. So no matter what the messages are, say attack or retreat, or yes or no, or I don't know, love or hate, or whatever, take any pair of messages, you won't be able to distinguish between the two. So this definition looks very strong. Is it achievable? Okay. Yes. Right. So here's, so both of you said basically the same answer, so it's achievable, right? So we know, or I guess that some of you at least know that you can use one-time pad. So what's one-time pad? Just take the key and XOR it with the message, right? So the key is as long as the message, and it's not hard to show that this thing is perfectly secure. Let me try to convince you. So if the key is a random string, then when you XOR it with the message, you'll get another random string, right? Because XORing is just addition over a group. Right? So when you take a random element from a group and you add it to another fixed element, you get a random element in the group. Same thing here. So you get here a random element, right? A random string. So you have a uniform string here and a uniform string here, so distribution is the same. Okay, it's achievable. We are very happy. No. So these are, okay, good question. So these are different, so here I define a distribution, and this is a distribution. So I'm not talking about random variables which work over the same world or something like this. So this is a distribution, right? I can define, like, I can write a histogram which says, for this fixed message M0, every ciphertext appear with probability P1, P2, etc. Okay? So look at this as a probability distribution. Again, here, I can look at this as a vector of probability distribution. Okay, so these cases are not the same. These are two different experiments, and then I compare the probability distributions. Okay. Good. So one-time pad achieves this definition. So this definition is achievable. But so this is the good news. The bad news is that what are the bad news? The key is very long, right? If you want to encrypt very long messages, and today we encrypt all the time very long messages, like gigabytes, and so on, then you'll have to share a very, very, very long key. In some cases it's usable, but when your message is longer, this thing is not practical at all. And unfortunately, you can show that this is inherent. So if we want to achieve perfect secrecy, then the key of the length must be as long as the message. So I wrote it to prove it as an exercise, but let me show you like a sketch of the proof, because I think that it works in, and at least in Israel, when you write something as an exercise, no one do it. So let me do it for you, but I have to erase this thing. Okay.
In your example, attack and retreat have different lengths?
No, so they are kind of, so the two messages have the same length. So
One's got 6 factors and the other 4.
yeah, so you pad them, right? I mean, so let's fix the length, canonical length of this thing, right? I mean, I cannot count right now, but the longest, okay, of the two, and then pad it with zeros. Or just write, I don't know, or something like this, right? Okay, so, so I want to show you that the length of the key must be as long as the message length. So let's draw a graph. So here we have the messages. So this is the first possible message and so on. So it's a bipartite graph, and here we have the ciphertext. So this is the first ciphertext and so on. And let's put an edge between these two guys with the key K. If when you encrypt M1 with the key K, you get the ciphertext, say C2 in this picture. Okay? And let's look at this ciphertext. So my first claim is that this ciphertext must be connected. So if it's connected to M1, it must be connected to all the other messages. Why is this true? So let's assume that there is some, I don't know, M10, which does not have an edge. So what does it mean? It means that when you look at the encryption of M10 versus M1, the distribution cannot be identical, right? There are some strings in the support of the encryption of M1, specifically the string C, which does not appear as an encryption of M10 because it doesn't have an arrow, right? So it means that every ciphertext here, which is connected to M1, must be connected to all the other messages. And now I claim that on these messages, you must have different keys, right? No key appears twice. Why is this true? Otherwise, you will have decryption error, right? If you have these two keys are the same, then if someone sees this ciphertext, then the decryption with this key is going to error either on this message or on the other message. Okay? So the number of keys must be as large as the number of messages. So that's what we wanted to prove. Okay? So this is, again, due to Shannon. So we have a very nice notion, a very strong notion, but it's limited, right? The length of the key must be as long as the message. All right. So what do we do now? So let's try to relax this notion and try to hope that we'll get something which is more efficient. So we already know what is the natural relaxation. Let's relax identically distribution to computationally indistinguishable. Okay, so now I require that for any pair of different messages, M0 and M1, of equal length, the ciphertext should be indistinguishable by computationally bounded adversaries. Let me remind you what it means. It means that for every probabilistic polynomial time A and negligible, there is some negligible function epsilon. So this slide should be updated, right? It's not for any A and any epsilon, it's for any A and some epsilon. The probability that A happens here and A happens there is at most epsilon, right? Okay, so, and I'm going to use this notation, this computational indistinguishability notation between the two experiments. Good. So now, there are two questions. So we have a new notion, and we should ask ourselves two questions. The first question is this notion, is it make sense? Right? Is it good enough for our applications? Does it capture the notion of secrecy that we want to achieve? And the second question is, can we achieve it, right, while having short keys? So let's start with the first point. So computational secrecy, which is also known as message indistinguishability. So this notion goes back to Goldwasser-Mikali in a very seminal paper. They got last year a Turing Award, and some partially because of this paper. And they also defined an alternative notion, which is called semantic security. And roughly speaking, I'm not going to define it formally, but it says that everything that you can learn efficiently from the ciphertext about the message can be computed without the ciphertext. So if you're an adversary who listens to the line, you gain anything by seeing the ciphertext. Okay? You can basically compute everything that you want. even without seeing it. So having the ciphertext does not help you at all. So I wrote it informally, but it can be formalized. And then the logic, as I said, is that therefore the ciphertext does not end any useful information for computationally bounded adversaries. And it's a nice exercise to formalize this thing, try to write it formally. It's not completely trivial. And it turns out that this notion of semantic security is equivalent to computational secrecy. So this gives us a very good justification for our notion of computational secrecy, right? It's a good notion because it captures exactly what we want on an intuitive level. Questions? Okay. Not for me. Okay, so computational secrecy is a strong notion, it's useful, it's great, but is it feasible, right? Can we achieve it with short keys? So the answer is yes, and we are going to use a computational analog of a one-time pad, right? So instead of storing our message, this is our plaintext, right, the message, with a truly random string, we are going to XOR it with a pseudo-random string, and our key is going to be the seed of the generator, right? So this is the encryption. The encryption is very simple. The key is the seed. And you're going to encrypt the message M by XORing it with G of K, where G is a pseudo-random generator. And to decrypt, you just do the same, right? Apply the pseudo-random generator on the seed K and XOR it back with the ciphertext. So this is what people, or a very simplistic form of what people call a stream cipher. Right? So you generate a stream of pseudo-random bits and then you XOR it with the message. So we want to prove that it's secure. Why should it be secure, at least in an intuitive level? Right, so if it looks like a random, and it feels like a random, and it smells like a random, it acts like a random even when you encrypt with it, right? So, and we know that if it was random, then it was secure, right, essentially. So let's prove it. So let me remind you, so I guess that you remember the definition of a pseudo-random generator, right? I mean, so you can think of it as indistinguishability of these two ensembles. Use a random key and then output the pseudo-random generator output, or just output a random string. So these two things are indistinguishable. So let's prove that our construction is secure. So the theorem says if the PRG is indeed pseudo-random, then this computational one-time pad is secure, right? Achieves the notion of security that we defined. So let's see the proof. So let's look at the ciphertext, the encryption of M0. So just by definition, this is just the value of the PRG applied to the uniform distribution, XORed with M0. Okay? And now, I claim that these two ensembles, if you switch this pseudo-random generator with a uniform string, then I claim that these two ensembles are computationally indistinguishable. Okay. Why is this true? We know that this thing and this thing are indistinguishable. Actually, I had a version of this slide where this thing was green and this thing was yellow. So I don't know why it changed. Anyway, so this thing and these things are indistinguishable, and I claim that this means that the whole thing and the whole thing here are indistinguishable. Why is this true?
You showed in general that you can apply any vulnerability.
Good. So we remember 2 hours ago we showed that when you take two things which are indistinguishable and apply some efficient randomized function, so this function is just a function which takes M0 and XOR it with this output, then you'll get computationally indistinguishable things. Okay? And now, this distribution is just the uniform distribution, right? When you take a uniform string and XOR it with M0, you get a uniform distribution. Good. And you can do the same, apply the same argument to say that the encryption of M1 is also computationally distinguishable from a uniform string. And now we can use another factor that we saw, right, transitivity, and we conclude that the encryption of M0 and encryption of M1 are computationally distinguishable, exactly what we wanted. Okay? Good. Questions? Okay, so naturally when I have an encryption, I want to encrypt many messages, right? I mean, maybe... So maybe I want to send one message today, M, and tomorrow I'm going to send M prime, and so on and so forth. So I want to achieve security even when I encrypt many messages. So let's see what happens with this nice construction that we had. So remember that to encrypt the message, and I'm going to just XOR it with the PRG applied to my key. And what happens if tomorrow I'm going to encrypt the message M prime? What will I learn? So for example, I will learn, specifically I can learn if the two messages are equal, right? I can just compare the ciphertext and see if they are equal. And more generally, as people just said here, I can learn the difference between these two messages, right? I can XOR the two messages together, and this part will vanish, and I will learn the XOR of M and M prime, right? So it's not okay to encrypt with the same key twice in this scheme, right? I mean, I will learn as I said, XOR of M1 and M2. And this seems like something which is clearly should not be done. It's really a bad idea, but actually people do it all the time. Okay, so one example is an old version of Microsoft Word, which used a very good PRG, right? The PRG was excellent, but they used it twice, right? When you did when you change versions of the document, like you said that to track comments. There is the track comments feature. So you encrypt it twice, and this way the whole system was broken, right? So, okay, so the people in Microsoft were not that smart at that time, but or at least the one who implemented, but
they were very smart and were paid.
Were paid, okay. I think that if they were smart enough to get paid for this thing, then they would do something less trivial. That's my guess. So I think that there are smarter ways to insert like secret trapdoors or things like that. So, no, really, this is something that you teach in like the first day of winter school in Bar-Ilan, right? I mean, so you shouldn't do it, right? But forget about Microsoft, so something here is fishy, right? I mean, we proved that it's secure, right? I told you that the definition is good and we have a construction, and we proved that the construction is secure, and it's in Beamer, it's not in PowerPoint, so really it should be correct. But still we see that this thing is insecure. So what went wrong? Right. So the definition. So we defined the notion of security for a single message, and it was great for a single message, but typically we want to be secure even when you have many messages. So we have to consider a new notion of security, a stronger one, right, which was for many messages. And in fact, if I'm going to strengthen my notion, I'm going to go even further and ask that this notion of security should be secure even against what people call chosen plaintext attack. So what does mean chosen plaintext attack? We'll define it in a minute, but I want it to be secure even in the case where the adversary can choose which messages are going to encrypt, right? By the way, are going to be encrypted by the honest parties. It's not. It's just that I already have like 3 notions of security in this talk, and I didn't want to go to 4. So if I had like in an infinite talk, I would say, okay, let's add multiple message. That's one step, and then go forward and define the CPA security, right? But I'm going to take this chance to upgrade my scheme, and I'm going to take 2 steps at once, right? So I'm going to immunize it against both multiple messages and CPA security. Right, so okay. So before we are going to introduce the new definition, let's reconsider the previous one. So this was our original definition. We said for every pair of messages, these things are computationally indistinguishable. Of course, this definition is somewhat, it's not fully formal. Do you see where do I cheat here? So this notion is asymptotic, and here this is a pair of messages. So if you want to be fully formal, you have to talk about ensembles of messages M0 and M1, which go for every length. And now you can define the probability distributions, like ensembles of distributions, and then you have computational indistinguishability. Right? But we're going to get rid of all these things by using an alternative definition. So this is the alternative definition. You have an adversary A, and the adversary chooses a pair of strings, M0 and M1. All right? And he sends it to a challenger. The challenger chooses a key, a random key, and then chooses a random bit. And then depending on the bit, he's going to encrypt either M0 or M1. And send it to the adversary, and the goal of the adversary is to guess what bit was chosen. Okay, this is similar to the game that we had in the pseudo-random generator definition, right? Can you distinguish between there that was green and red or something like this? So can you distinguish between the case where you encrypted M0 or M1? And as before, this is equivalent to the previous definition. And you can think of it as a student who chooses on which strings to be tested, right? So the student chooses the test, and then you're going to test him, and then you're going to measure its success. And note, as before, it's always possible to guess this bit with probability half. So we're going to say that to define security by saying that for every efficient adversary, the advantage is at most half plus negligible. Okay? And this thing is essentially equivalent to the previous definition that we had. So this is still for a single message, no CPA security, right? No chosen plain text attack. Good. And it's a nice exercise to try to prove the equivalence. Okay. So now let's extend the game and define CPA security. So what do we mean by this? So now we give the adversary more power, which makes the definition stronger, right? Because the adversary is more powerful. So the adversary can ask for encryption. So he sends X1 and gets an encryption of X1 and X2, encryption of X2, and he can do it adaptively. So once he saw this encryption, he can choose based on this value X2 and so on. So there is the blue phase where he just kind of practice, right? He learns some things about the encryption, how does an encryption of 0 looks like, and so on and so forth. Everything under this key. And eventually, after seeing all this blue part, he's going to ask for a test, right? Depending on what he saw so far. And now we are going to check whether it succeeds or not. Okay? So we have two phases, the phase where we adaptively choose encryptions, and then the test, and we should distinguish between the encryption of 0 and 1. Okay. And again, the security will say that for every probabilistic polynomial time adversary, the probability of guessing the right bit is at most half plus negligible. Okay, does it make sense?
Is the MI to be different from the X?
Hmm?
Will the M to be different from the X?
Good point. So, what's your name? Ido. So Ido says you need the M's to be different than X. What do you mean? Please expand.
If you want to challenge the M0 and M1, you just ask beforehand what are the encryptions.
Okay, so you are claiming that this definition is maybe nice, but it's not achievable because someone can just choose this M0 and M1, right? Ask what is the encryption of these guys, okay? And then once he has the ciphertext, he's going to ask, please test me on this M0 and M1, right? It's like asking the questions for the exam before the exam, right? And then you can see whether the ciphertext equal to the case where he used the X0 or the cases he used the M1, right? So it seems that we have an attack, right? We show the general attack against this notion, and this notion cannot be achieved. Okay, so think about it for a second. We'll see in 2 slides that the attack fails. But think how to bypass this limitation, right? So we have a pseudo argument that says that this notion cannot be achieved because you can always attack him, right? The attack is clear?
If it is deterministic.
Good. Okay, so some of you already know the answer. Let me just say about the definition before we are trying to break it and see that the break does not work. So it's always possible to guess the bit probability half, and this notion says that this definition says that you cannot do much better than that. Okay. So before we talk about feasibility, let's talk about the usability, right? Is this thing useful? And the big question, when you show this definition to, at least to some people, they say, this is crazy. Why do you grant the adversary so much power? Why would the adversary be able to see messages, encryption of a message that he chooses, right? I mean, you said that Eve is sitting on the line. How can Eve tell Alice to send these messages to Bob, right? That's essentially what happens here. So, do you have a good answer for this point?
On both sides. Yes.
Signatures, but we are not talking about signatures.
Insiders.
What?
Some insiders.
What if?
Some insider. They can give you information.
Insider.
Some insider. Okay, insider is a good answer, although, you know, if you have someone from inside, he can just give you the key. So it's kind of... So the point is that, so there are two answers to this concern. The first one is, you know, as cryptographers we want to take big safety margins. But actually there is a better answer than this one, and history tells us that actually yes, it happens that the attacker has some form of encryption oracle. Right? So this is encryption oracle because you can ask to encrypt some messages. And let me give you one example. There are actually many nice examples for this phenomena. So for example, say that you have some servers, they communicate with each other. The communication between the servers is encrypted, but they encrypt, you know, things which are related to requests that are sent by the users, right? So as a user, I can just, if I want to see an encryption of some value, I can just inject requests that correspond to this value, and I know that the servers will talk to each other and they will send this request, my request, encrypted, right? So there are many scenarios. So in this scenario, I can see encryption of messages that I want, that I sent, right? I can determine which messages are going to be encrypted, and there are many examples like this. So it's not an overkill, right? Asking for CPA security. In fact, towards the end of this talk, we'll ask for something even stronger. Okay, so here's a remark. I guess that it's related to David's point previously. So we could define an intermediate notion between, so we talked about CPA security so far and ciphertext indistinguishability for a single message. So a purple notion will be a ciphertext indistinguishability for multiple messages. So this is strictly between these two things in the sense that this purple notion is weaker than the red notion, so it's strictly weaker. You can find schemes which satisfy the purple but not satisfy the red definition. And it's strictly stronger than the blue thing. So you can find, you can come up with construction which satisfy the blue thing but does not satisfy the purple one. And again, it's a nice exercise to try to formalize this intermediate notion and see, show all these implications and separations. Okay?
CPA?
What?
CPA stands for?
CPA is for chosen plain text attack. Yeah, this is our current notion. So, okay. I'll try to keep it as long as I can. So, so here's the theorem following the attack that was suggested before. So the theorem says if the encryption algorithm is the deterministic function, so it just depends on the message and the key, then it is insecure. Right? It cannot be secure under chosen plain text attack. Even if the adversary makes only one CPA query, so your attack had 2 CPA queries, but I can use only one. So I improved your result. So I can, I can just ask you for M0, the encryption of M0, and then choose a random M1. And when I get the challenge, I just compare it, is it equal to the encryption of M0 or not. Okay, so this is somewhat disappointing. But how can we bypass this theorem? Right. So we have 2 ways to bypass this thing. So one way is to use randomness. So whenever I encrypt a message, I'm going to use fresh random coins. So an encryption of a message, unlike the intuitive notion of encryption, an encryption of a message is not a single ciphertext by a bunch of but a bunch of ciphertexts. So there is a big collection of ciphertexts. Each of them is potentially an encryption of the message using this fixed key, right? And this set of possible ciphertexts should be large enough, super polynomial, such that even if I try to see many encryption of the same string, I'm not going to see the same encryption twice, except with very small probability. Okay? So this is one solution. The other solution is to use state. Right? So if I have a state and I'm going to keep update my state, then when I encrypted the M0 in the morning and now when I encrypted it in the afternoon, I will see different ciphertext because my state has been changed. Right?
Then you wait to the next morning.
What?
You wait until the computer refreshes.
No, it's not the computer refreshes. Once I encrypted, I change my state. Okay? Every encryption changes my state. Okay? It's not about the time, it's about the mechanism, right? So this algorithm keeps a state and the state is is updated, and the state again should be long enough such that if you see many encryptions, you won't see the same encryption twice. So the period should be very large, super polynomial. Okay, is it clear? So today we are going to talk mainly on randomized encryption, but this stateful encryption is actually being used when you use a stream cipher. In many cases you actually use a state, right, and you update your state. So you can fix the problem with the pseudo-random generator, the construction we show, by introducing a state. Think how. Okay, so let's try to construct an encryption scheme. So far we talked about definitions. And let's for a second forget about efficiency. So if you don't want to be efficient, there's a very, natural solution. So let's assume that Alice and Bob share this huge random object, right? A truly random function from n bits to n bits. So what do I mean by random function? I mean that, during the morning, right, before the evening, these guys chose for every possible input x, they chose a random string, a random n-bit string, which is going to be the image of x. So they use many coins, they toss them in the morning, like, right, and for each of these 2 to the n values, they chose n coins, which determine the output here. Okay, so we have a truly random function. It's a huge object, it's very inefficient, but we don't care about it for now. So let's say that we have this thing. How can we encrypt? So, I don't know, the obvious thing to do is just to apply the random function on the message. Of course, then you should ask how do you decrypt, and let's assume that this function is invertible. So let's assume that it's 1-to-1 or a permutation from n bits to n bits, right? So we can invert this function, so we can encrypt and decrypt, and the question is this thing secure? So now we have 2 notions of security. We have indistinguishability under a single message, and we have CPA security. So what do you say? Does it satisfy both notions, one of them, none of them? It is deterministic, very good. So it's a deterministic, although we choose a huge random object, okay, once I chose this, you can think about it as a very long key or something like this. Once I chose this encryption is deterministic. So it cannot be CPA secure. Specifically, if you encrypt the same message twice, you'll see the same ciphertext. Right? You'll see the image of M twice. So it cannot be CPA secure. Is it indistinguishability for a single message? Yes, right? So if I'll give you a single message, then I won't be able to distinguish between, say, M0 and M1. And in fact, it's going to be secure we can define a notion which is CPA prime secure, and CPA prime secure will say that the adversary can send only a different message at each point. We cannot repeat the messages. So if the adversary cannot repeat the messages, then this thing is going to be secure as well. Right? Okay, so the question is how to achieve, but we want to achieve this CPA security even when messages are being repeated. So how can we do it? How can we do it? Okay, we should use somewhere randomness, right? I mean, we know that it cannot be deterministic. So our current construction says, this is the space of messages, take your message and, go forward, and this will be the ciphertext. So a very, a reasonable solution would be, don't encrypt the message, but randomize the message and then encrypt the randomized message. So don't encrypt this point, move to a random location, right? XOR it with some R, and then encrypt this point. Okay, so this is exactly the construction that we're going to see. So to encrypt a message M, choose a random string, right? A random difference. And now shift your message by R and send the encryption of this thing and also send this shift vector R. Okay? And decryption is easy. Just invert the function on this point and shift it back to R. Right? That's encryption. To M. That's the decryption. Okay? And I want to prove that if f is indeed a random function, that this thing is CPA secure. So let's prove it. So, okay, so the proof is simple, but it gives us a chance to understand the definition. So what does it mean? Let's assume that you have an adversary which breaks the scheme, or let's fix an adversary and try to see what can be the advantage of the adversary, right? So we have an adversary which makes polynomially many queries. Okay, so let's name this polynomial by t. And how does this adversary look? So the ith query is going to send some xi, this is the message, and this xi is going to be encrypted by some ri, and ci, which is encrypted over xi, shifted by ri, right? So these are the values that this adversary sees, Ri and Ci. And then comes the challenge phase. So this guy chooses a pair of strings, M0 and M1. And let's denote the ciphertext that corresponds to MB, right? We chose the challenger chose the random bit B. This is the challenge bit. And let's denote it by R star and C star. Okay. So I want to define a good event, and that's actually something that happens in many security profs. So we care about a good event. We're going to say if the good event happens, then everything works well, and this good event happens almost always. That's like a general outline. So let's fix all the randomness up to the phase that this R star is being chosen. The randomness that is used to encrypt the challenge. So everything is fixed. And now the good event is that the event that when you look at the XOR of R star and M0 and the XOR of R star and M1, this thing does not equal to a value that we already saw. Right? We saw the adversary saw all these values, XI XORed with Ri. So we saw many points. Right? There is a collection polynomially many points and their images. Okay? And let's hope this is a good event that these 2 points, right? I can define these 2 points, don't fall in this set. Right? They fall outside of the set. So what is the probability that this event does not happen? So the size of the set is T, so the probability that this thing does not fall into T, and the probability is taken over R star right now, is?
Poly over exponential.
You can be concrete. Who said poly? So we have T, right? So it will fall here, right, with probability T over 2 to the n, right? And it will fall here with probability T over 2 to the n. So altogether, this event, the good event happens, probability 1 minus 2T over 2 to the n. And this quantity is negligible because T is polynomial. Okay? So the good event happens almost all the time. That's good. Okay? And now, if the good event happens, that I claim that we are in good shape. Why? So let's try to think as the adversary. So the adversary knows all these points, but outside these points, the function is truly random for the adversary, right? And you can imagine an experiment where you choose the random function, the values outside of this area, only at this point, right? Like lazy sampling. And now, if you do this, then these random variables, conditioned on everything that you saw, everything that we fixed, these 2 random variables are uniformly distributed the same, identically distributed, right? They are uniform over the set of all the values that we didn't see. Right? Remember that this is a permutation. If we were dealing with a function, then I didn't have to, the proof would be slightly simpler. So it's not completely uniform over 2 to the n because I know that it cannot be equal to these values. This function is permutation, but also it's uniform over the values that I didn't see. Okay? So this means that in this case, right, you cannot distinguish between the encryption of M0 and M1 with probability better than half. Right? Information theoretically. So that's it. Now we can finish. So what is the probability, the winning probability of this adversary? So the probability of winning condition on G times the probability that G happens, the good event, plus the probability that G does not happen. If G does not happen, then, you know, all bets are off. Let's say that the adversary always wins. Right? I'm just interested in upper bound. So this thing, right, winning condition on G is half. G happens with probability 1 minus negligible. Let's increase it to 1. Right? It's an upper bound. And this, so we have this half. And this thing happens with negligible probability. So we have an upper bound of half plus negligible. Okay? So the details don't matter that much. I just want to highlight again the structure. So we identified a good event, and we said, okay, this event is very, very common. It almost always happens. And assuming this event or conditioning on this event, things go well, right? You cannot break the scheme.
For the encryption to be reversible, you must have it on both sides. So
what do you mean, have it on both sides?
if you had an Alice and Bob, you'd have to have the encryption reversible still. So you would have to keep state of your random.
No, I don't understand. So I assume that they chose that permutation. So they have the permutation. Both of them have the permutation. It's an inefficient scheme. I will get to an efficient scheme in a minute. Okay? But this is an inefficient scheme. They both share a huge random permutation. Right? It's invertible. They can invert. They can do everything. So everything here is information theoretically. As long as the adversary, as long as the adversary does not make too many queries. Okay? Okay, so, but, this is very expensive, so we want to, to have an efficient scheme, and instead of using a truly random function or a truly random permutation, we're going to use a pseudo-random permutation, right? That's kind of natural. So let me remind you, so this is a PRF, so you shouldn't be able to distinguish between these two boxes. In one box, whenever you input an X, you get the value of a random function from n to n, or permutation. And this is the pseudo-random case where someone chose a key, right? This is a collection of functions, and when you insert X, you get the function applied to this X. Right? So you are given, so this is the definition of pseudo-random functions, pseudo-random permutations. Iftach told us about it an hour ago. Right? Okay. So here is the efficient construction, right? So we have an inefficient construction, here is the efficient version. So the key is going to be the key of the collection of the function. Right, the name of the function from the collection, a random function from the collection. And to encrypt the message, I'm going to do exactly the same thing that I did before. I'm going to shift the message by R, where R is some random string, and I'm going to apply the function on this point, and I'm going to reveal this shift vector. And decryption is done in the same way. And the theorem will say, well, previously the scheme was secure, and now when you replaced a truly random object by a pseudo-random object, the scheme is still secure. Right? So let's prove this theorem. Again, it's not hard. So we're going to convert a CPA attacker, A, with success probability half plus epsilon, into an epsilon prime distinguisher for the pseudo-random permutation. So we say if you can break the encryption, I can actually break your pseudo-random permutation. So here's the adversary B. So B is given an oracle, right? So a box, a black box, this G. And G is either a random function or a truly random, or either a pseudo-random function or a random function. So how does the reduction looks like? So we invoke the algorithm A, right? We have to use it. And now A sends us a CPA query, right? A query wants to see the encryption of a string X. What are we going to do? Send it to our oracle as is. So we're going to try to emulate the true encryption, right? So we are going to choose a random shift vector and going to send the oracle the shifted message, right, by R. And we are going to claim that this is a ciphertext, right? Ri, comma, this value. So we are going to answer all these queries as we should. And then given a challenge, a pair M0 and M1, right, we are going to generate, we are going to toss a coin. This is the challenge bit B. We are going to send encryption of MB, right, as before. Choose a random R star and shift this MB by R star and plug it into the function, and that's it. And now, what are we going to output? So this adversary A is going to output some bit B prime. What are we going to do? We're going to check if B prime equals to B. Right? So if B prime equals to B, this adversary succeeds in breaking this object, then I'm going to say this object is pseudo-random. Right? So I'm going to output 1 if A's guess is correct. And the intuition, we'll see it in a minute, the proof is one line, but the intuition is that if this oracle is a truly random function, then I know that this event happens with probability roughly half. Right? But we know by assumption that if G is a pseudo-random function, then this guy presumably breaks this encryption scheme, right? Probability half plus epsilon, therefore we get an epsilon distinguisher for the new, for the PRP. Right, so the proof is actually just what I said. So when B works with the pseudo-random function here, so this is exactly, this is a perfect emulation of the game where A tried to break this scheme, the real scheme, right? So this thing happens with probability half plus epsilon by assumption. On the other hand, if I plug in the random function, right, then we showed in the previous slides that the probability that was anyone, forget about B, forget about A, any adversary that runs in polynomial time can break it with probability at most half plus negligible. Right? So we know that the gap between these two quantities is at least half plus epsilon minus this half plus negligible, so we get epsilon minus negligible. So if we could break this thing with probability, I don't know, 1%, then you get almost 1% here. Right? With one, that's the gap. So it follows, since we know that the PRP was secure, it follows that epsilon must be negligible, and therefore this adversary cannot break the original scheme.
You provided some toolbox to simplify proofs. Like, for example, if some two things are indistinguishable and you apply some transformations and it's the same.
Right.
You just extend it to some.
I could. I could extend these tools to the case where you work with oracles. So this game is with Oracle. That's why I couldn't use the tools as I stated them. But I could say that if you have an Oracle access, you're an efficient algorithm, and you have an Oracle access to an ensemble of function which is indistinguishable from another ensemble of functions, then A to the F should look the same, or as A to the G, right? If these are to F and G are the ensembles, I could do that. Yes, it's true. But then I had to prove the fact. So this is essentially the proof. Okay. So, an alternative construction, so the previous construction was based on pseudo-random permutations. We know that we can build them very efficiently using Luby-Rakov, but still here is an alternative construction which uses only pseudo-random functions. So it's a weaker primitive. And now instead of shifting the point here, we are going to shift it in the output. So I'm going to choose an R, go forward, right, compute this f of r, and then XOR it, use it as a pad to the message. Okay? And I'm going to output the shift vector again. So it can be shown, and decryption is done in the natural way, right? So in order to decrypt, I can apply this f on r, I know r, and then I'm going to XOR it with c. So this is decryption, and note that here I don't have to use the inversion algorithm. So the function can be pseudo-random function and not a pseudo-random permutation. So this is nice, and you can prove that if this function is pseudo-random, then this construction is CPA secure, right? It's not hard to prove it. In fact, it's somewhat simpler than the proof that we just saw. Okay. So questions for so far? So pseudo-random functions, pseudo-random permutations typically work on like fixed length blocks, say 128 bits, right? So people talk about AES, so we can assume that AES is a pseudo-random permutation, and that's the input length of AES. But typically we want to encrypt longer messages, right? Not only 128 bits. And the question is how to encrypt longer messages. So we have a good encryption that works for a single block, but we want to extend it to many blocks. So there is a very simple solution. What's the simple solution? Just apply it to each block separately, right? So this works, but the rate will be poor, right? I mean, the length of the ciphertext will be twice as large as the length of the message, right? For each message, remember, in both constructions that we saw, we outputted like a pair of values, right? This shift vector and this padded block, right? So we output per single block M, we output 2 blocks. So if we do it per each block, then it will be somewhat expensive. And ideally, we would like to have, when the message is very long, something whose rate is very close to 1, right? We would like to avoid this blow up of a factor of 2. By the way, note, just a side remark, we said that randomness is crucial for security. Note that we didn't use private randomness here, right? I used randomness, but the randomness was public. I transmitted it over the line. So it's not that usually when you say randomness is crucial, we think that the randomness should be hidden. But in this case, the randomness is not, the secrecy is not the point. The point is of avoiding repeated sequences, right? So the randomness was public. It's an important thing to notice. Okay, so we have a poor rate, and if a solution has a poor rate and want to improve the rate, ideally to rate 1 or something which is very close to 1, and it turns out that it's possible. So this is called the CBC mode of encryption. I always forget the initials. So what are the initials? Right. So B and C are for block chaining, right? So for block chaining, I don't know why it's chaining. I don't understand, but there are like. Yeah, but when the XOR is here, then you call it in a different name, right? So the names are not. I don't know. Okay. So how does the CBC look like? So you start with a random block here, And then you are going to, in the first block, we're going to just imitate the construction that we already saw. So I'm going to shift my message, and I'm going to encrypt it and get the ciphertext. But then, in the next blocks, I'm not going to use a fresh randomness, I'm just going to use the previous block to shift the message, right? So I'm going to encrypt the ith block by looking at the previous block of the ciphertext, shift it, and then plug it into the pseudo-random permutation. Okay? And decryption is done in the natural way, right? I can invert this thing, I have a decryption algorithm, and then I'm going to XOR it with the block and recover the value of this block. So this is, this S0 is called the initialization vector. Sometimes people write it as IV, and it should be a random seed, right? You have to choose it at random, and you send all these blocks plus this random block, right? This is the ciphertext, and when the message is long enough, the overhead is a single block, and so think of many blocks, so the overhead is kind of negligible, right? It's almost like the rate goes to 1. Okay, when you use a new message, so this sequence is a message, right? It's a long message. When you use a new message, you have to use a new, fresh random seed. Why?
Otherwise, the ciphertext will have to first do.
Right. Otherwise, you will have the same problems that we saw before, right? For the same reasons that we saw. So you have to choose here a new random seed. You can use what people call counter mode, right? Just increase the counter of this thing and preserve a state. That's what I said, right? Previously, that instead of using randomness, you can use also state. So this will also avoid collisions, right? But if you don't want to keep a state, you have to choose a randomness every time that you encrypt. Okay, some properties of CBC. So encryption is inherently sequential, right? So let's go to the picture. So if you want to generate this block, you have to go through all the generation of all the previous blocks, right? Because this block depends on this one, and this one depends on this thing, and so on. So it seems that encryption is sequential. On the other hand, what about decryption? So decryption is kind of parallel, right? You can decrypt only this block by looking at inverting this function, look at the previous block. So you don't have to decrypt all the prefix in order to get the last block, for example. So encryption is sequential, decryption is parallel. It's standard in many systems. I guess that we'll hear about it in the following days. It can be proven that if E is a pseudo-random permutation, then this mode is secure in the CPA sense. I'm not going to prove it. The proof is non-trivial. The intuition is that if this thing is indeed a pseudo-random function, then this blocks indeed looks like a random pad, right? I mean, you apply here the block cipher, or there's this pseudo-random permutation, so this value looks like a random string, and therefore you can use it as a padding value, right? By the way, so far we talked about pseudo-random functions and pseudo-random permutations. Essentially, when you say pseudo-random permutation and block cipher, these things are essentially the same. Okay, so I guess that, I don't know if later you're going to use the block cipher terminology, but this is the practical name for pseudo-random permutations. Okay, so that's what I have to say about encryption for now. Yes, please.
There might be a problem with what you said, counter mode, because maybe you can change the plain text in a way that cancels the advance of the counter. So, and then you may be able to notice that. So counter mode should be used with care. It's not like crazy.
It's true. So the fact that you can predict, you're saying that the next value. I don't, as far as, so right now I don't think that it leads to a bug, but I reserve the right to say differently tomorrow. So I don't think that it leads to an attack. I think that you can prove that the counter mode will be CPA secure, but maybe I'm wrong.
If you change just one bit here and then the corresponding bit in the plain text, then the change would cancel.
No, but you don't have, so okay, so one important point is that you don't have, I'm not giving the adversary control of this thing. So this thing grows by 1. So
one bit changes. In half of the cases, it's just one bit change, and you know where, in the LS bit. So you can change the LS bit of P1 by 1, and then the XOR would be the same as the previous message. C1 would be equal in both cases.
Okay, I have to think about it. So this thing is going to be fed to the PRP. Okay? So a 1-bit change here can do like magical things after you insert it in.
But what he said is that you first encrypt as 0 and then 4 and then it's fine for me.
Okay, I didn't follow the fix, but I don't think that the fix is needed. As far as I remember, counter mode is right.
You can do it in parallel. If you make the ID a counter, that's not counter mode.
That's not?
It's not counter mode.
That's not, right.
No, you have to encrypt typically counter.
Right.
Store that with the message.
Right. Okay, good. You have to encrypt the counter, that's true. Okay. So I'm not sure, so I guess that my variant, I'm not sure whether the variant that, as I stated it, is insecure or not. I have to think about it, but it's not what the counter mode is. Right, okay. It's insecure, good. Okay, so here you have an answer for from the experts. Okay, so so we talked about this thing and we wanted to move to message authentication codes. Okay, so take a deep breath. So we are changing the subject, not completely, but somewhat. So let's change the setting, and now we have Alice and Bob, but our adversary now is, does not care really about the content of the messages. He's trying, in a sense, to impersonate, right? He's trying to hurt the integrity of the messages. So the adversary listens to messages. The messages are not necessarily secret. And now is active adversary, so we can change bits along the line. And the goal of the adversary is to so the adversary listens to many genuine conversations, but then eventually he's going to send his own forged message, and he's trying to fool Bob to think that this message was sent by Alice. Okay, so think of, I don't know, two lovers, and they send all these love letters, and this friend listens to all these letters, and then eventually she tries to forge a message and says that, I hate you, right? I mean, Alice, right? So Alice should be able to detect, or Bob should be able to detect that this is not a genuine message, right? That's the story that we have right now. So how do we achieve this goal? So our tool is going to be message authentication codes, and there's an important remark. So authentication, the way we define it so far, is orthogonal to secrecy. Okay, there is no, right now at least, there is we don't care about secrecy. So maybe all these messages are public, and you don't care about having your love letters, published on the web. It's just that you don't want someone to change the content of these letters, right? Okay, so what is authentication codes, or message authentication codes? So the idea is to have to let Alice and Bob share a secret key, and Alice is going to append the message some authentication tag, okay, some function applied to this message M, which depends on the key K, the secret key K, in a way that allows Bob to verify the integrity of the message. So Bob is going to check that indeed this tag is consistent, right, with the function and the key, and it should be hard for friend to generate false messages with these tags. Okay, so here is like the syntactic definition. So we have a message space, typically the set of all strings, and we have a secret authentication key, this M-bit string K. And we have an authentication algorithm, which is a mapping from a key and the message M into a tag. And again, we allow this thing to be randomized, although typically, well, it's not clear that it has to, unlike the case of encryption, which can be deterministic. And typically this tag is going to be very short, much shorter than the message, and again, for efficiency concerns. So clearly this function is not one-to-one. Why? Right, so Gilad has a very concise answer. Right, the output is shorter than the input, therefore it cannot be one-to-one. Okay, so it's a many-to-one function, it's compressing. So there are many messages which are mapped to the same tag, right, under a fixed key. And to define security intuitively, what we want is, we would like to, it should be hard to forge a valid tag of a message without seeing the message, right? Without seeing a tag on this message. Okay, does it make sense? Okay, so let's define it more formally. So the notion that we have is going to be existential forgery under chosen plaintext attack. And we said that the MAC is secure if for every probabilistic polynomial time adversary A, And what is the power of the adversary? The adversary is allowed to ask for polynomially many legal pairs. So the adversary can ask, give me a tag on this message, M1, M2, etc. He can choose the messages adaptively. And at the end, after he saw all this message, the goal of the adversary is to come up with a new red message that he hasn't seen so far, together with a valid tag. Okay? So we say that this thing is secure if every polynomial time algorithm fails or succeeds with no more than negligible probability. Okay, so the probability is taking over the choice of the random key, and if the adversary is randomized, also over the randomness of the adversary. Note that the adversary chooses the messages, so again, it's a strong notion, right? It's a chosen plaintext notion. And note that again, as in the case of encryption, we are taking a big safety margin in the sense that we consider it a success even if the message on which the adversary was able to forge a tag seems, I don't know, meaningless, right? You could say only if the adversary was able to forge a meaningful message, then you consider it as an attack, as a successful attack. But this is bad because it's hard to determine what's meaningful and what's not meaningful, right? I mean, maybe something when you interpret it as a ASCII string, then it's meaningless. But when you think about it as an encoding of Excel file, then suddenly it becomes very meaningful, right? So we don't care about how does the string look like, as long as it's a new string. It's a forgery. Good. So one trivial thing that the adversary can do is just to guess the tag, right? So the success probability is going to be 2 to the minus L. Another trivial thing is to guess the key, right? If you guess the key, then you are going to succeed with probability 2 to the minus N. So these are trivial attacks, and they mean that the key and the tag cannot be too short, right? So they have to be long enough, much shorter than the message maybe, but not too small. So let's try to construct these things. And when we try to construct these things, it's useful to stand on the shoulders of giants. So let's think of Shannon, for example. So what would Shannon do, right? I mean, forget about efficiency. How would you authenticate if there's no efficiency concerns? So what would Shannon do? What? Use? One-time pad. Okay, that's actually, that's not the right answer, but I'm very happy that you said it. So it's a good example of an encryption, which is a good encryption, a good one-time encryption, but very bad pad. Right, I mean, so imagine that I'm going to send my message, right, encrypted in a one-time pad, right? So this is like I don't know, the tag, right? It's a long tag, but let's ignore this point. So it's very easy to generate a tag over a related message, right? I can, for example, flip one bit of the message, of the tag, which means that this tag corresponds to the message where this bit was flipped in to the original message with this bit flipped, right? So one-time pad, when you see a tag over one message, it's very easy to generate tags on related messages. So this is not good for us. So what would Shannon do? Use a random function. Good. Random functions are great, right? We already know that. So here is a almost trivial claim. So if you have a random function from n bits to L bits, then it cannot be broken with probability better than 2 to the minus L. It's a great MAC, even if the adversary is unbounded. Now remember that success for the adversary means that he was able to generate a tag on a new message, right? So why is this claim, so how do you prove this claim? So let the adversary see many MACs, right? If the function is random, then it's a point which is not queried before, right? This is the random function. So if we have a point for which the adversary didn't query, then the probability of guessing the value of this point is 2 to the minus L because the function is truly random, right? The value of this point is truly random, conditioned on all the adversary, or all the knowledge of the adversary. Okay, so this is indeed a trivial claim. So now we know how to construct a MAC. How will we construct a MAC? If a random function worked, then what will work as well? A pseudo-random function, good. So we're going to use a pseudo-random function, much more efficient, still secure, right? So here's a very simple theorem of not hard theorem. A PRF is a secure MAC. Okay? And the proof idea is that if the PRF was truly random function, then it would be hard to forge. Therefore, an adversary that breaks the MAC allows you to distinguish a PRF from a truly random function. So I can do it formally. I hesitate. Okay, let's continue without the proof. So I think I guess that any of you can now prove it by itself, right? I mean, it's a 4-line proof, and it's not easy. It's not hard to do it. Okay. So there's a problem here because the PRF is defined for a fixed length blocks, right? Again, as we had in encryption. So the question is how to support long messages, right? How do you authenticate long messages? Any idea?
If you're Shannon, then you can hold the PRF for each length.
If you are sure, even if you are Shannon, I mean, you fix your, these guys share this function, right? I mean, now they cannot reshare, like, function is a fixed object, right? I mean, okay, so I suspect, okay, now I have the slide here. So here are a few suggestions, let's see. So we want to extend the max to many blocks. So we have a long message, right, M1 to ML. And we want to define a MAC that works for all these messages, assuming that we have, say, a pseudo-random function from n bits to n bits. So I think that I saw, like, using hand, someone suggested a construction, right? Construction by hand, which was something like this, right? So just apply it blockwise. Is it a good MAC? No. Why? You can, okay, again, answer by hands, right? You can swap the order of messages. Okay, that's a bad thing, right? I mean, I can see a MAC on the message, and then I can generate a MAC on the related message, which is just with different orders of blocks, right? I can reorder these blocks. So let's try to fix this. How will you fix it? CBC is an advanced solution. There is like indices. Good, very good. Okay, so let's just write, authenticate the block and its index, right, together. So now you cannot rearrange, right? I mean, who did the rearrangement? It doesn't, I didn't say that it works. I said that you cannot rearrange. Okay, so why this thing fails? Okay, good, right. I mean, so again, the answer is by hands, right? So let me try to imitate you. How did you do it? Like this, right? I mean, so you can have like two messages, like right, M1 and M2. This is the first message, and M1 prime and M12 prime. And you can you can generate a MAC on this in this new message, right? So this is bad. How do you fix this problem? It was a good thing because I didn't give you the slide on this on your booklet, and therefore you cannot cheat in this case. Not CBC, without CBC. What?
Use previous results as keys for.
I don't want to use states. You're right. I can use states and do something which depends on the state.
For the length of the message in the first block.
The length is not the issue right now. The point is, the problem is that here. So all the messages are of the same length.
This is ID and an index.
Okay, good. Very good. So I'm going to choose a random identifier, this R. Okay, and I'm going to send this identifier and authenticate each block with the identifier and the index and the block. Okay? So this R is carried over all these points.
Why does it fail?
Because here I will have one R, and here another R, right, with high probability. This R is long, right, it's n over 3. Right, so you cannot mix things. So now we cannot rearrange, we cannot mix, but what we can do now? Truncate. Right. I can throw away the last block here and get a new authentication of the prefix of the message, right? And sometimes think of your emails. A prefix of the email can be very different from the whole email, right? I can give you examples.
You speak like you.
Okay. So that's here's another solution. Let's add the number of blocks here. So the number of blocks is L, so let's authenticate each block separately, together with the random identifier, the index, and the length of the number of blocks. Is this secure? This process does not converge, right? I mean, we add things. It's like when you write an exam, right? You solve and then you fix your solution, but you don't get anywhere. So is it secure or not? I can duplicate blocks. How do I duplicate blocks? No, they have an index. If they duplicate this block, then the index kills you. Secure or not? Is it secure? So it's secure. Okay, so right, you can't. I mean, it's obvious, right? I mean, you can't rearrange, you can't drop things, you can't mix. No, you can prove that it's secure. It's not hard to formally prove that this thing is secure. So in this case, really, the thing that we did capture all the attacks. So good. So we have an authentication scheme for long messages, but there is a problem with this scheme. What's the problem? Well, it's polynomial time, but the tag is very, very long, right? It's very inefficient. It's actually longer than the message, right? I mean, so here I used n bits for only n/3 size blocks. So it's going to be like 3 times or 4 times larger than the message. This is a disaster, I'm being told. So we want to have something more practical. And now we get to CBC MAC. So there are basically like 2 widely used solutions. There's CBC MAC, and we'll see it in a minute, and there's a solution, say HMAC, which is based on cryptographic hash function. I'm not going to talk about this thing at all. Okay, so let's go back to MAC. So this was the MAC, right? I mean, take your block, sew it with this IV, and then apply the encryption or the PRP, the block cipher. And we're going to do the same, except that we're now going to start with an all-zero IV, so it's not randomized. And instead of outputting all these Cs, I'm going to output only the last block. I'm going to produce all these blocks, and at the end I'm going to discard all the n-1 blocks and output only the last one. So this is the MAC that I'm going to have. And this is widely used in practice. It's very efficient, like PRP is a very fast primitive, and it has a very good rate, so although the message was very long, the tag is going to be relatively short. So it works very well. There is this nice question of replacing this all-zero string with a public random string. What do you think? Okay, it will be good or bad, or we don't care. It's bad. It's bad. Think why, right? It will be very bad to replace this thing with a random string. Okay, but there is nothing like holy about the all-zero thing. Just fix one constant and use it all the time. Okay, so there's a theorem which says that this construction works well as long as all messages have fixed number of blocks. Okay, so I'm not going to prove this theorem, but again, let me state it again. So assuming that you have a pseudo-random function, this CBC MAC is resilient to forgery as long as all the messages that the adversary uses have the same length. And actually, this restriction to equal length messages is not a problem of the proof, it's a problem of the construction. So let me show you quickly why this, so the proof is by using reduction. We are not going to talk about it. But let me show you quickly what happens when you have different lengths. Okay, so there's basically the picture tells the story. So let's assume that I have this authentication, this tag of that corresponds to M1. This is C1, right? And now remember that I can adaptively choose my next message. So I'm going to ask you to authenticate the message C1, right? The tag that I saw. So I get an authentication C2. Now I claim that this block C2 is a valid tag on the message 0 and 1 all 0. Right? And you can see easily why, right? I mean, let's look at how the tag of this message is going to be computed. So here I have the all 0 XORed with M1. I'm going to have here C1. Okay, so this is true. And C1 XORed with all 0 applied, if you apply E here, I get exactly C2. Okay? So I can actually, if as an adversary I'm allowed to use different length, messages of different lengths, I can actually break this scheme. And you can generalize it to every number of blocks, right? I can, this is not just a case of a single block versus 2 blocks or something like this, or 2 versus 3. Okay, so how do you solve this problem? So there are several solutions. One solution is to start with the number of blocks at the beginning. So you can show that the previous problem happens only when you have 2 messages with equal prefixes. Right? So here, right, this message is the prefix of this message. That's why I have a problem. So if you don't have these messages with equal prefixes, then you are fine. The construction will be secure, and that's a way to force it. Right? Just add the number of blocks at the beginning, you get a prefix-free coding of the message. So that works well. The drawback is that you have to know n at the beginning. So if you think of these blocks as coming from some source, then you cannot work here online, right? You have to know in advance what is the number of blocks that is going to be authenticated. There's another solution, which is to put n at the end, but this is insecure. Okay, so you have to be careful about this solution, or in other words, it's not a solution. And there is the most standard solution, which is, it looks kind of weird at the beginning, so you're going to do the standard MAC, and then you have a single block. This is the last block of the CBC MAC, and then you're going to encrypt it by using another different key. So the overall key of the MAC is going to consist of a pair of keys, right, K1 and K2. And this is almost as efficient as the original scheme, right? I mean, you just add another application of a block cipher or a PRP, which is typically fast, and you can prove that this thing is secure. Okay. Questions? Okay, so we're getting near the end. So there is the issue of combining authentication and secrecy. So we know how to authenticate, we know how to protect secrecy, at least against the cipher CPA, in the CPA notion. And in some cases, we want to combine these two things together. All right? So there is a question, say that you want to have authenticated encryption. So I'm not going to define this notion right now, but think intuitively, I guess you can imagine something. The question is how to combine encryption and MAC. So here are a few suggestions. So one of them will be to encrypt the message and then apply a MAC on the message, of course using different keys, so there will not be dependency and so on. So is this thing secure? Yes? Right, so maybe the MAC reveals the message, right? You can easily construct maybe artificial MACs which actually reveal a lot of information on the message. So it's not going to be secure in general, right? Maybe for some schemes it's going to be secure, but in general, right, if all that you know about this MAC is that it's a MAC and all that you know about this is that it's encryption, it's a bad way of combining the two. Okay. What about this thing? So this is somewhat more tricky. So let's authenticate the message, append this authentication to the message, and then apply the encryption. Is this thing secure? Depends. So depends for me is no, right? For us in theory, right? So you can prove that in some cases the thing works well. Maybe you'll talk about it. Okay. So you'll hear more about this thing, but not in general. Okay, this thing may be problematic. It's less immediate to see why, but I'll give you a hint in the next slide. And finally, there is this, I guess that the third alternative is to encrypt and then authenticate, right? So you encrypt your message and then apply the authentication code on the ciphertext. What about this thing? Secure. Right. So this is secure in general, right? No matter what the MAC is and the encryption scheme is, the thing is secure. And we'll go back to this scheme. Actually, it achieves a very strong notion of secrecy, and I'm going to show you in a minute what it achieves. Good. So let me say a few words about authenticated encryption or combining this notion of authentication and encryption. So in some cases, even if you care only about secrecy, then you want some form of authentication. So let me give you an example. So imagine that Alice has an M bits message, M, and there is some noise over the channel, right? So Alice wants to correct the errors and also achieve secrecy, right? So Alice is going to do the following thing. She's going to send a message bit by bit, right? So she's going to encrypt this bit and so on. So now M1 is the ith, or MI is the ith bit of the message. And also she's going to compute the parity check of the message and send an encryption of the parity check, right? Just in case there is some noise over the channel. Right, and now Bob decrypts, and if he sees that the parity check does not match, he's going to shout and send an error message. Right, please send your message again, or something like this. So I claim that an active adversary, which is allowed to change bits on the line, can completely recover the message. How? How can he recover the first bit? what? He can? Okay. No, but this thing is a long ciphertext. So let's say the following thing. So let's try to do something easier. So let's say that he knows that the last bit is always 0. Okay, let's assume this for simplicity. So you know that this bit is the last bit is 0 because it's some, I don't know, some standard information that is going to be passed. So he's going to do the following thing. So he's going to take this this encryption of 0 and he's going to swap the first bit with the encryption of MN. Now what's going to happen? If this thing is an encryption of 0, then everything will work very well. Bob will say, I'm fine with this message, because the parity check bit, will be fine. But if this is an encryption of 1, then the parity check is not going to be correct, and Bob will shout, there's a decryption error, right? Or I don't know, error on the line, whatever, syntax error. So now the adversary learned whether the first bit is equal to the last bit, right? And he can do the same trick using all these bits for the second bit and so on and so forth. Eventually we learn like whether each of these bits is equal to the last bit. And if he knows the last bit, then he's fine, he knows all the message. Otherwise he can guess the last bit, probability half is going to learn the message. Okay. So you see that in this context, CPA security is not enough, right? There is an attack here which is not covered by CPA security. You can show that this scheme is CPA secure. And in fact, this is not just a funny story that I invented. There are some real-world scenario which looks essentially like this, right? Okay. So here's a stronger notion of security, our last notion of security for today, which is CCA security, which tries to protect from such an attack. So this is still CPA secure, right? In CPA secure, the adversary sends many messages and is allowed to see the encryptions, and then is going to be tested on the red pair. And now we are going to strengthen this thing. So what is CCA security? So the adversary is allowed to send blue questions, right? I mean, give me the encryption of X1 together with decryption queries. Please decrypt for me this Y1. Give me a decryption of 1.1, and so on. So he's allowed to ask for encryptions and decryptions. That's why this is chosen ciphertext attack, right? So he has an oracle for decryption, and he can use this oracle, and then he gets the test, and in fact he can further use the oracle after the test, as long as he's not asking to decrypt this system. Okay, so this is our definition. So decryption queries can be also asked after the challenge, after seeing C star, as long as they are not equal exactly to C star, because if you're asking for a decryption of C star, the whole game becomes trivial, right? You cannot achieve this, you cannot achieve security. So this is a very, very, very strong notion of security, right? The scheme should be secure even if you're allowed to see, to have an access to a decryption oracle. And I think that it's really strong. I mean, it's kind of surprising that you can even achieve it. And in some sense, it captures this situation that we saw previously, because in this parity check bit story, this adversary had a partial access to a decryption oracle, in a sense, right? This error message of Bob gave him some information about this ciphertext. Does it decrypt nicely or not? Okay. So it turns out that the construction that we saw, this encrypt, then authenticate, achieves this notion of security. So assume that you have an encryption scheme which is CPA secure and the MAC, right? Then you can define a new encryption scheme which is basically the encrypt then authenticate. So encrypt the message and then authenticate the ciphertext. And let's define the decryption as follows. So if the MAC is correct, then decrypt. Otherwise, outputs, I don't know, a special bottom symbol or something like this. And you can prove that the new scheme is CCA secure, assuming that the MAC is secure and the original scheme is CPA secure. So it gives you a very efficient construction of a CCA secure encryption scheme, so it achieves the previous strong notion. I'm not going to prove it, but let me give you, I don't know, a few words about the intuition. So again, we are going to somehow define like a good event, and we're going to argue that almost always the good event happens. So let's assume that we have a chosen ciphertext attacker. We're going to say that if you have a good CCA attacker, then you can somehow either break the MAC, or break the CPA secure encryption scheme, right? One of the components. So let's call a decryption query useful if it does not equal to an outcome of a previous encryption query. Right, so let's go back to this picture. So so this thing is useful if it's not the outcome of some encryption query. Right, if it's the outcome of encryption query, then I already know what is the plain text of this Y2. Right? So if this Y2 appears here as a blue value, then it's in some sense it's not useful for me. I could have done it by myself. Right? So this is the notion of useful queries. And now you can show that useful queries with almost always answer with null. Right? Otherwise you could have broken the MAC. Right? Because being able to generate a useful query means that you were able to send or a useful query which is not answered with this bottom means that you could generate a MAC on a ciphertext which on which you didn't see the MAC before. So this corresponds to a MAC forgery. Right? So if you were able to generate a useful query which is not answered with null, then you can break the MAC. And if you didn't, then basically you didn't really use your decryption oracle. Right? All the decryption oracle gave you is values that you can emulate by yourself because they're not useful, or just nulls which you can also emulate by yourself. So eventually you broken the scheme as a CPA secure scheme, right? You have an attack which breaks the scheme in a chosen plaintext notion. Okay, so you can formalize the thing. It's not that hard, and it's a beautiful and very efficient construction. Okay, so let me conclude. So we saw many different levels of security for encryptions. There are other levels that we didn't cover. Authentication is orthogonal to secrecy. It's an important lesson to remember, and the combination is somewhat tricky. Okay, things which looks okay may not be okay. In general, MACs and encryption schemes can be based on pseudo-random functions or pseudo-random permutations, or as you call them in practice, on block ciphers. These reductions, both the construction and the security reductions, are very efficient. So these are practical transformations. So these are, I guess, the main building blocks that you need for symmetric cryptography. Once you have them, you can do all sorts of things. It's also, we saw that I guess during the day in several points, not only in this talk, that it's a very good design methodology to start with, to try to reduce a complicated task to a very simpler task. Right? So, we want an encryption for many, many blocks, but maybe it's better to start to assume that you have an encryption for one block and then try to extend it into many blocks. And now let's try to, let's try to think of how to construct an encryption for a single block and so on. Right? Eventually, in all this, we saw today, we didn't see all the details, but that you can reduce a very complicated object such as CCA secure encryption scheme to a very basic object like one-way functions. Right? So we skipped many of the details, and some of these results were cited, but this is, I think that this is a big success of this methodology. It works both in practice and theory. Okay, and that's it, I guess.